Hello and welcome to Designing Better ML Systems, Learnings from Netflix. My name is Rob Hilton. I'm a Principal Solutions Architect with AWS, and I'm joined by Netflix's very own Savin Goyal, a software engineer from their machine learning infrastructure team. Netflix has been a longtime AWS customer and open source proponent, and for the last decade or so, they've been focusing that lens on the wide world of data science. In today's talk, we're going to discuss some of the decisions, infrastructure decisions that Netflix has made, and also some of the open source projects that help ease the burden on their data scientists. And we'll also step through what it will take for you and your organizations to get started building these similar systems. In order to kick it off, I'm going to hand it off to Savin.
Thanks, Rob. Netflix has made significant investments over the years in machine learning, and we are constantly looking for ways to improve our machine learning systems. Now, what does that mean for us? How do we go about getting this meaningful improvement? Yes, of course, one way is to invest in getting more and better data, as well as innovating on building bigger and better models. Yet another approach that my team focuses on is how can we provide a modern data science stack to our data scientists so that they can go from prototype to production as quickly as possible and can be as productive as possible. Now, in this talk, I'm going to talk about how we think about a data science stack and what does that mean internally at Netflix and some of the open source work that we have done in that area. And my expectation is that hopefully some of these thoughts would be useful for you as well as you go about building similar infrastructure at your companies. Now, what does the infrastructure stack look like? It's ultimately at the end of the day composed of layers of pre-existing stack that any organization that is collecting and operating data operates on. At the very bottom, we have a story around data warehouse. Then we need some sort of compute resources to manage and orchestrate your compute. And of course, data scientists, they are very well familiar with notebooks. That's their lingua franca when it comes to authoring any sort of machine learning code. So we need to have some sort of notebook infrastructure for them as well. And all of this should allow for rapid prototyping, rapid model development without essentially enforcing any sort of constraints on their day-to-day work. Now, what does that look like for Netflix? At Netflix, S3 serves as our data lake, our data warehouse. All of the data that Netflix ingests is available when it comes to tabular data as Parquet files exposed as iceberg tables, as well as it serves as a repository for all the TV shows and movies that we shoot around the world that's available to our members. Now, using Amazon S3 as our data lake has paid off significant benefits for us over the years. It has allowed us to decouple compute from data storage, which means that now we can invest in different querying engines, different compute engines, and we can move as the industry moves. So we have invested in Presto and Apache Spark. And all of these are exposed through our federated query engine called Genie, which is available as an open source project so that our users, they have a unified interface through which they can launch these jobs without actually worrying about how to locate a Presto cluster or which Spark cluster has access to which data sets for them. And all of the data sets are managed, all the metadata around it are managed and exposed through Metacad, so our users can very easily discover all the data that's available to them within the Netflix universe, and then they can meaningfully query that. Now, when it comes to machine learning workloads, there's one behavior that we observed internally, which was most of the times our data scientists are actually interested in getting access to a single or multiple partitions of one single iceberg table, which means that going through a query engine like Apache Spark or Presto might actually at times be not as efficient as, say, directly going through S3 and saturating your network bandwidth to pull the data as quickly as possible. So internally at Netflix, we have invested a lot in building these tools that allow our users to short circuit a bunch of these query engines so that then they can feed their data to their machine learning workloads as quickly as possible. And a lot of this innovation is actually available as part of our open source tooling around Metaflow. Now, once you have these machine learning workloads which are able to reliably ingest these data sets as quickly as possible, the next question comes that, hey, how do you execute these machine learning workloads? Where does it actually run? Does it actually run on a user's laptop? Does it run in the cloud? And yes, of course, for quick prototyping, we want our users to be able to run these workloads on their laptops. But then there comes a point where they need access to GPUs, where they need access to higher memory and higher CPU cores than what's available on their laptops. And that necessitates a move to the cloud. At Netflix, our container orchestration system is called Titus, and a close parallel to that would be AWS's Batch. And this allows our users to very efficiently take their code that's running on their laptop and be able to launch these containers at scale. Now, what's interesting about these machine learning workloads is that they can be rather bursty and resource intensive. Now, think about this use case where, say, as a data scientist, you want to train a model for every country and every language that Netflix operates in. So we are already talking about roughly 2,000 or 4,000 different models, depending on the permutations. Now, if you want to do a hyperparameter sweep over each of these models, now we are looking at 10 to the power 5, 10 to the power 6 models in expectation. And that places a huge load on our container orchestration systems, and it can meaningfully starve out other workloads that might have higher priority. And that's where careful resource management becomes really, really important for us. Both Batch and Titus expose queuing mechanisms where a machine learning workload can very efficiently queue tasks. And then these queues can leak these tasks based on priority onto the actual container orchestration system, say Elastic Container Service or Kubernetes. And that allows us to very meaningfully isolate some of these machine learning workloads and make sure that they don't end up impacting any of our production workloads. At the same time, for many of these machine learning workflows, cost efficiency is a very key concern. Many of these training pipelines, they end up using GPUs or other exotic instances, which can often be super expensive. And also, for our end users, it can be really hard to estimate the resource requirements for any of these jobs ahead of time. So we have invested in machine learning models and other systems that can accurately predict what are going to be the resource requirements for any of these jobs, so that then we can much more efficiently pack these jobs onto a physical instance so that we can drive up utilization for our workloads, and which essentially then ultimately at the end of the day helps us in driving down cost. Now, once you have all of these workloads running, and a machine learning workflow, as we just spoke about, can be rather wide. Now we need to think about, like, okay, how do we actually orchestrate each of these individual jobs? You can have a machine learning workload that's processing a terabyte of data that needs access to an instance that has, say, terabytes of RAM. Then maybe once you have done feature engineering on that data and you have sort of like whittled down your data, then you might want to offload the compute to an instance that has GPUs so that then you can train your model. And then you might want to sort of like move your compute to a general purpose instance where you can just like characterize what the model quality is. And that's essentially the role of an orchestrator. And the orchestrator that we use internally at Netflix is Netflix's Conductor. And a very close AWS offering is AWS Step Functions. Now, when we look at a machine learning workflows, some machine learning workflows are meaningfully different than, say, data engineering workflows or other ETL batch pipelines. More importantly, machine learning workflows, they can be rather long. Say, if you're, say, training a computer vision model that needs to crunch through all the frames that Netflix has ever collected, that can take weeks to execute upon. So we need to make sure that the orchestrator has support for long-running workflows, as well as at the same time, these machine learning workflows, they multiply rather quickly. Netflix is a big believer in experimentation. So any change we push out, whether it's a change in our model or whether it's a user-facing change, we always run multiple A/B tests. So we need to run multiple instances of the same pipeline in parallel with minor little changes to test out that, yes, of course, the newer model or the newer sets of models are indeed better than what's running in production right now. And we have many data scientists, many teams working on many different problems. So the number of machine learning workflows that are running at any given point in time, they can very quickly multiply. So we need to make sure that our workflow orchestrators can also scale well for us. And in practice, we have found AWS step functions and conductor to really scale out for us in a very meaningful manner. Now, one thing that's really important when we think about machine learning workflows is that these workflows are not isolated islands. They are essentially consuming data from, say, an upstream data engineering ETL, and then the model that they produce, that needs to essentially connect to some downstream process that might be consuming that model, say, hosting it as a microservice or, say, generating some offline scores. And it's really important to have some capability to think through how would we sort of like piece together these different processes, these different pipelines. And that's where data signaling comes in really handy for us. In open source, in AWS universe as well, an equivalent offering for configuring data signals would be event bridges, where say you have an upstream data engineering pipeline, and as soon as it's done writing to a table, it can emit an event, and then you have like a bunch of other pipelines, your machine learning pipelines, which are waiting on those events, and then they can trigger on top of that, which is a much better mechanism than, say, polling for a given sort of like timestamp to trigger your pipelines. Once you sort of like provide all of these capabilities, like the other thing that data scientists care about is, what is my authoring experience? How do I actually go about writing these workflows and getting through my ideas? And we have made huge investments in the notebook ecosystem internally at Netflix. If you are using Python or R, then you can very easily spin up a Jupyter notebook and you can get access to any number of instances that AWS provides to run your compute in the backend. As well as we have yet another open source project called Polynote, which allows users who are more interested in the Scala and JVM ecosystem to get the same benefits of the notebook ecosystem. Now, when you are running machine learning workloads as a data scientist, monitoring and observability is a key issue. You would want to know how is your model behaving over time. The ML workflow that you just launched, how is that behaving? You would want to inspect the model that has just been produced, which essentially calls for some sort of ML monitoring solution. And in our experience, it's actually rather tricky to build a monitoring solution that can take care of all the different diverse set of problems that teams at Netflix are trying to solve. The model monitoring requirements for a problem in natural language processing is going to be very different than, say, if you're solving a computer vision problem. And what we found was rather interesting for us was notebooks by themselves can be an interesting mechanism to monitor your machine learning pipelines. The data scientists, they are already well familiar with the notebook ecosystem, so they can very quickly and easily put together these dashboards that can investigate and look into how their workflows are behaving. And what we do internally at Netflix is we allow our users to essentially set up these templatized notebooks that are executed by a paper mill and are hosted as dashboards in Commuter. And both Papermill and Computer are open source projects. So for example, in this screenshot, we have a user who is just tracking overall execution time of different steps of their workflow using Boca. And there's like nothing specific about any of the internal tooling for our end user, and they can essentially take care, they can use any open source libraries that are available for visualization. They can use any sort of widgets that they are comfortable with, and they can customize this notebook for their use case. So this is what a modern data science stack looks like nominally at a very high level. For data warehousing concerns, Amazon S3 is an excellent choice. And AWS Batch gives you access to the latest and greatest instances that Amazon has to offer for compute. And through step functions, you can very easily piece together your workflow to execute on top of these batch instances. Via SageMaker notebooks, you can author your workflows in a very easy manner. And then none of these layers prevent you from using any of the latest and greatest innovations that are happening in the open source community, whether it's MXNet, TensorFlow, PyTorch, scikit-learn. Now, all of this is all good and fine. These are like the basic building blocks that are indeed needed for any sort of data science activity. But there are still some things that are missing from this picture. As a data scientist, you still have to worry about how do I actually write my workflow? Do I need to familiarize myself with Amazon state languages to be able to use step functions? Do I need to learn how to bake Docker containers so that I can launch my jobs on AWS batch? Do I need to be familiar with how the data is laid out in my data warehouse to be able to interact with it? As well as there are a bunch of machine learning concerns as well. Experimentation and versioning is a big concern in machine learning because of the iterative nature. And you would want to make sure that any sort of experiments that you do, any sort of changes that you make to your model, they are captured reliably and you're able to go back in time and replay those. Reproducibility is yet another big concern, and you would also want to make sure that you're able to very reliably train multiples of models and you're able to manage those effectively. So, which means that at the end of the day, you also need some solution that can sort of like bind these layers together so that as an end user, you can focus on more of the data science work and less of the engineering work, which is what Metaflow provides. So Metaflow is a Python library that we have written over the last few years that has really helped us understand our data scientists' pain points. And we have taken all of our learnings through those years and baked it into an opinionated package that allows our data scientists to focus more on the model development aspects while all the orchestration, compute, and data movement aspects are taken care of behind the scenes for them. Now let's look at like what are some of the major features that it provides you. So it allows users to write idiomatic Python code to declare their graphs, which means that they are free to use any of the libraries, any of the training packages like TensorFlow, PyTorch, Scikit-learn. They can use any of those. They can even write their own training routines. We bundle in a high throughput data layer, which allows them to then access S3 and essentially saturate the entire network bandwidth that's available to their instance so that then they are not paying heavy costs just around moving data. We provide very simple primitives so that our users, they can very easily declare that, hey, this is my workflow and these are some specific jobs that maybe need access to an instance that has high memory or an instance that has GPU instances attached to it. And they can very easily just drop in a bunch of decorators, and then Metaflow will take care of how to orchestrate that compute and move their data as well as code to those instances, perform the compute, and move back the results to the next instance that's waiting for the input. And once they have all of this done, and once they are happy with the model that has been produced, then if they have to sort of like deploy their workflows onto an orchestrator like AWS Step Functions, then it's a one-click task for them where Metaflow will essentially compile their workflow down into a language that Step Functions will understand so that our end users, they don't really have to worry themselves with learning yet another DSL to integrate with any of the orchestrators. And more importantly, we also manage and maintain all the metadata that's generated through every single execution of these workflows, which allows our users to then set up these notebooks and they can track how their workflow is behaving, what are the characteristics of their models, what is the distribution of the data that went in, and they can use any sort of widgets, any libraries like Boca, Plotly, Dash to set up these dashboards. And of course, a model doesn't live in isolation. It needs to integrate with an external service. So they can very easily just follow a function as a service paradigm to define functions that can be used for either offline batch scoring or can be hosted as microservices. And all of this functionality is also available to the users in our language as well. So these are some of the features of Metaflow, as well as some of the architectural and technological choices that we have made over the past few years that have really paid strong dividends for us. And now Rob will walk you through how to get started with all of these infrastructural choices within your own AWS account. Over to Rob.
Thank you very much, Savin. Now that we have an understanding of the infrastructure that's required in order to build these types of ML systems, let's step through the process of building it together, shall we? Fortunately, it's relatively easy. There are only a few teeny tiny little prerequisites that you need in order to get an infrastructure up and running that matches AWS best practices. First and foremost, we know that we're going to need to store artifacts. So let's create an S3 bucket. Secondly, we need compute. So let's create an AWS batch compute environment. Don't forget to enable EC2 provisioning mode. Third, we're going to create an AWS Fargate ECS cluster. Don't forget to enable inbound access and security groups for port 80. That's important. Third, we're going to create a Postgres database. Your schema is going to need to be, hold on, okay. So I got away from me a little bit there. Let's go through these one by one. We're going to need an NLB. We're going to need some DynamoDB. Okay. Did you create your task definition yet? There's a Lambda. Okay. Okay. Congratulations. I guess we're done. Your infrastructure is ready. If your eyes glazed over at the beginning of that last slide, you're not alone. In the world's least surprising plot twist, AWS infrastructure gets complicated and difficult the more nuanced a solution becomes. But fortunately, AWS and Netflix have done much of the hard work for you. There's an open source CloudFormation template that you can find at github.com/netflix/metaflow tools. That open source CloudFormation template should deploy most of the infrastructure that you need from A to Z that allows you to stand up these ML systems and start seeing them work for your environments. There's an added benefit of the fact that this CloudFormation template is inherently flexible. It covers multiple different types of configurations, meaning that if your environment needs to do prototyping with Jupyter notebooks, that's an option for you, whereas you can turn it off if you don't. Additionally, if you need things like GPU instances, those options are available to you as you deploy this infrastructure. Secondarily, we've set it up so that it's secure. The permissions are restricted to the environment that is deployed by CloudFormation, so that means people won't be accessing infrastructure that they don't need. And last but certainly not least, due to the relationship that we have with Netflix, we ensure that we maintain feature parity in the infrastructure as Netflix discovers ways to enable their data scientists across the board. Now, let's dive a little tiny bit deeper and explain what this CloudFormation template is going to do for you as you stand up. First of all, I want you to imagine with me a big, empty, lonely AWS account. There's nothing in it. And then you start with the CloudFormation template that we talked about last time. The first thing that we're going to need to think about is whether or not our data scientists need to prototype. If they do, then we're going to be able to stand up Amazon SageMaker notebooks, and then you'll have a flexible Jupyter environment that has permissions already set for the rest of the AWS infrastructure. Secondarily, we know that we're going to need asset storage for our flows, and we also know that we're going to need compute infrastructure, so the CloudFormation template will stand that up for you as well. But we're starting to get into a little bit of a nuance here in the fact that in order to maintain security across our environment, AWS Batch will need to be able to pull from S3 safely and securely. So we'll set up all the IAM roles and permissions for that. Speaking of IAM, we'll also create AWS IAM users that only have permissions to access the resources configured within this CloudFormation template. Additionally, if we spin up different versions of this CloudFormation template, we'll also get standalone users that don't have the ability to hop around in environments where they don't need to be. So now that we have this environment stood up and functional, and we understand that we have our basic infrastructure resources, we have to think about how to scale these things. So what we'll allow you to do is, instead of scheduling and orchestrating these flows with your laptop or machine, we'll configure AWS step functions for you along with all the permissions so that you can schedule pipelines and flows and orchestration steps and have them triggered. Now, it's a big world for organizations out there, and as Savin mentioned, it's very, very, very likely that your pipelines and machine learning systems don't exist in an ether or in a vacuum. So we have the rest of AWS, so the CloudFormation template will configure everything that you need from Amazon EventBridge in order to facilitate integrating your pipelines and flows with all the rest of the other cool stuff that you are doing. As if that isn't enough, it's configured so you can easily stitch it together with Amazon Service Catalog and expose these services to your end users for deployment as they see fit. Now, this all makes an assumption that you are working in a production environment with your AWS accounts. But what if you just want to get started and see how it works? Fortunately, Netflix has used a variation of this CloudFormation template to allow you to get started all without any of your own infrastructure under the covers. You can go to metaflow.org/sandbox, you can sign up with your GitHub ID, and you can get a restricted sandbox environment running on AWS that allows you to get started with Metaflow and see if these types of systems work for your organization. With that, that's the end of our talk. Feel free to go and check out any of the resources and documentation or open source projects that you've heard about in this discussion. And on behalf of Savin and myself, thank you so very much for attending.